Kiddos just joining us. Maybe it's because you're a slacker, maybe it's because you're absent. We have a few of those. Those who are not here, we just checked all of our homework. We're not going to do it again in detail. So if you need these answers, pause me. Hey, there's some. There's some more. There's some more. And there's the rest. The end. See? I can do it. Okay, here we are. Section 9.7. Probability. Yesterday we got down this formula. I think you guys had time to write this, right?
Yeah.
Roughly. The long story short of probability with all this vocab, yada, 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 is probability, the chances of, the number of ways something could occur, a certain condition could be met, a favorable outcome could occur out of the total outcomes. And we brought up like playing cards yesterday. I know Mr. Che was talking about like blackjack with the kids in the sense of, don't you want to somewhat think about probability as to what card, whether you should, what's it called, hit or yeah, hit or pass.
Stay.
Yeah, I didn't think it was called.
No, it's stand. Stand.
Stand? I thought it was stay.
No, it's staying.
Either way. Whether you should hit or not. Hey, I got that one down. Okay, so you want to think about probability and those sorts of things. However, there are many more applications to probability as well. Some people, when you're thinking about, I don't know, whether it's races or whether it's like baseball or whether it's when you're trying to say someone is due, that's usually baseball, isn't it? Like they're due because it's been so long since, et cetera, et cetera, et cetera. That's probability, which usually that's incorrect probability. But the number of ways something can happen out of the total number of outcomes. So moving on. Just to get our mind wrapped around the small numbers, because in section 9.6 you had huge numbers for a lot of those, how many ways something could happen. It sounds like, oh my goodness, there are so many ways until you think about the total number of ways, which could be so much larger, and hence your probability or chances could be so small, right? Hence you should probably never play the lottery seriously. Anyway, so let me back. It's like bankrupting countries. Not quite America yet.
Yeah, but
When we go down to the Dominican Republic and the different like villages that we go to in a specific locale, which isn't in the immediate city, it's a little bit more out. There are all kinds of these little like bancos, and we're like, oh, what are these little banks? Like, why are there so many banks? And we thought they had made money, and they're like, no, it isn't being places. And so really, all the guys get money, and then they go spend it, or they go drink it away, and their families are like stuff. Anyway, danger, danger. Might sound good. Doesn't mean it always is. Life lesson. Okay. If the probability of something occurring is 0, you should never do it because the event is impossible. So the event will struggle. Now I'm going to have 3 words, not occur. I'm not exactly sure the original 2 words I meant to put there, but that's okay. Will not occur. E is an impossible, sorry, I'm just doing an impossible event. Orientation. Okay. If probability equals 1, oh, okay, that's a pretty good probability. I mean, it's 1. No, actually, it's kind of low, isn't it? No. 1 is the best probability because it's 1.00. 1.00 is what percent?
100%.
Nice. So we'll call it thanks. Must occur. Now, that doesn't exactly lead into the next 2 questions, but it was just one quick little note to add underneath probability of P. The numbers will look a lot different because they are decimals, percentages, etc. So, example. Let's go back to coins. Were we ever at coins before? Maybe we were. Well, let's go to coins, and then we'll go back to cards, which we were talking about yesterday. Alright. Just like in section 9.6, sometimes the easiest way to figure out probability, if you can hold it all in your head, is to go ahead and think about what are all the different ways it can occur, and then how many of those are beneficial, profitable, favorable for what they're asking. So you toss 2 coins, right? What's the probability that both land heads up in the idea of counting up all the different options, all the different ways you can toss 2 coins? Let's assume they land on a side. On a face. Is that better? Okay. Question. Someone's actually question. You guys keep going. How else could you get? Tails, heads. What else? Heads, heads. What else? Tails, tails. Oh, no, I did that one.
Heads, tails.
Heads, tails. So how many total options are there? Total outcomes is 4. That would be the sample space. Okay. What are they asking as far as the favorable condition or the event or the outcome that they want to happen? Okay. Out of those 4, how many times will heads, heads be there? 1 out of the 4. And then Tyler already jumped and said, hey, 1 out of the 4 is going to be the same thing as 0.25 or 25%. In homework, you're checking the back of the book. Sometimes decimal, sometimes a percentage, sometimes a ratio. You guys should be able to equate them all and see that they're, like if you have a fraction, they have a percentage, you have the right fraction down that represents it. Does that make sense? Help Jacob out, it's a rough day. Okay, letter B. Letter B. You draw 1 card at random from a standard deck of playing cards, aka no jokers. You guys, we talked about it yesterday. Jason helped us out. How many cards in the standard deck? 52. What is the probability? Okay, we asked this one. What's the probability you get an ace? 4 out of 52.
1.7%, 7?
Which is the same thing as 1 out of 13. Why does that make sense? Why would those be the same?
Because there's 13 cards in it.
Yeah, there are 4 different suits of 13 cards each, and 1 of each of those 13 is mixed. All that to say. This is correct. That is correct. Has anybody found me a percentage just so we can say that's correct?
8%? Round it up.
Okay. I'll take it. Probably should. Approximately 8%. Okay, and math, we should actually be somewhat. Yep. Okay. So, not sure if I like them odds. Okay, so ready? Let's keep going. We got some important words to talk about. Yeah, some important words to talk about. One of them we've already seen, which is the nice thing. And. Awesome. There are a few different ways in which and can be applied, be used. And depending on how you're thinking about a probability problem, you might need to consider it 2 different ways. One way that we have seen and already is, this is a quick review, fundamental counting principle. Can I do FCC? Where we have one event occurring and another event occurring, like a first and a second. That was fundamental counting principle and. In the sense of choosing a 3-digit number, you choose the first digit and the second digit and the third digit, etc., etc., etc. And that's kind of what's going on down below in the sense of probability of events A and B occurring, but we could also be talking about characteristics. We could also be talking about characteristics. Something like, what's the probability that kids in this classroom are wearing jeans today and have brown hair? Okay. You can have all the kids in the room wearing jeans stand up. All the kids having brown hair stand up. I'll be like, oh wait, really? You could. I know you're all lazy, so we'll stand up. But jeans people could stand up. People with brown hair could stand up. But is that really what we're asking? Should we multiply those 2 numbers together? No. We're looking for narrowing down the field and saying, oh, hey, that's why I brought in the Venn diagram. If we're talking about shared characteristics, a better way to think about shared characteristics might be, instead of like, hey, you're taking these 2 separate and multiplying them together because you have to do both, this is a little different in that you're talking about, what was our example? Wearing jeans and having brown hair. We would have each of our different people out here that are wearing jeans, but not brown hair. Each of the people with brown hair, but not wearing jeans, But what we have in the middle?
Both.
It died. Oh, it died. Does that mean the video died too?
No, the video
No,
just sees
it's
exactly
still-
what you see
Oh, that's
on the screen. It is kind of sad, isn't it? Hold on, it's still there. Maybe it'll come back to life. Guys, what's the middle of a Venn diagram represent? You saw that drawing. I was like putting little dots. Yeah, which one has both? And the ones that are outside on the gene side or outside on the hair side, what's going on there? They only have one of the characteristics. So just think about the and in two different ways. In the sense of shared characteristics, think about it more like a Venn diagram. It's just thinking and thinking and thinking and thinking. But if we're talking about one event occurring and another event occurring, not a shared characteristic, then perhaps we'll still be using multiplication. As I'm pulling it, trying to pull it back up. Does anybody remember the snazzy math term? I mentioned it briefly in section 9.6 that and is indicative of. It's an upside down U. Multiplication is the operation. Do you remember the snazzy math term? I think it probably showed up when you were doing like logic stuff. If A, then B, like in geometry. Not specifically in this context. Intersection. Okay, just in case we can't get it to come up. Oh, now that I did all that. Okay, so Venn diagram, remember the inside is the ones that have both, the people that have both. That could be seen in this and seen in that. If you start bringing in a third condition, people in the very, very middle are the ones that share all three. Now they're both loading at the same time. Hope it doesn't crash again. Kiddos, let's go ahead and write down the formula though for intersection while we still have notes on the screen. Snazzy upside down U. A and B. If we're not just talking about shared characteristics, if we're talking about two separate events more similar to our fundamental counting principle that we're kind of more used to. Upside down U. It means the probability of A and B occurring. A little upside down U is a symbol for an intersection. So A intersection. We're going to go ahead and say the probability of A happening times the probability of B happening, which the nice thing is pretty similar to what we saw with the fundamental counting principle, in that we would multiply the two separately. Find the chances of A happening, find the chances of B happening, and then multiply the two. However, I do need to change this just a little bit. I'm going to put B such that A. Now that's weird. It's a little straight up and down line. It's not BLA. It's like an absolute value. Maybe I'll make it a little bit more obvious. B such that A. Such that A has occurred. Let me give you a quick example. Is there 2 R's or 1 R?
One.
No, there's two.
It's the curve.
Cured. If you cured something, it's C-U-R-E. That's also occurred. I feel like
Well,
it's,
listen to Ricky. He's like half asleep.
but 2 R's don't look right. That's, I was about to do it. Does it depend on whether we're in Britain or whether we're in America?
Uh-oh, did it crash?
It's double C for sure.
Oh, sure, yeah.
Like journalism people, anybody?
What?
We'll just keep it. Okay.
It is
For
2
example,
R's.
this does not always make a difference. Just because A has happened doesn't always mean that B changes. So let me give you a quick example of when this is true. Let's say you have a dual engine plane. Okay, sure. And you get two identical engines.
Good crash.
It's two R's.
Thank you.
I just said that.
Ricky's
He said it first.
Okay. Let's say we have a dual engine plane. Let's go back to my example.
No, feels bad.
No, that's not worth that one.
We should go back more than that.
It's all over.
Yeah, pretty close. Where am I at? No. Ooh, there's a Venn diagram. Is that the right one? Haha! Okay. You guys have it written down, it's there. Probability of A times probability of B. But sometimes probability of B might change based on A occurring. You get a dual engine plane, you get two engines that are identical in the sense of not the same exact engine, that'd be one, but two of the same type, bought by the same production company. And they say we have, the engines are, what should I say, efficient, accurate. You can't think of the right term for it. But the chances that's going to fail are like 0.0000 whatever 1%. That's great and all. That's ideal. That's them testing one engine for the normal workload it would have in a dual engine plane. However, what if you're up there and one engine goes out? Would the probability be the exact same as the manufacturer stated on the other engine now that engine 1 has gone out? No, why not? Or why? Why would it have a different probability?
They're counting on both engines working together.
Exactly.
If one engine goes out, it's more likely that the other one will.
Because the plane is built in order to be supported by two engines, and so when one goes out, the workload just got harder on the other ones, and the probability just rose that that one would go out as well. Does that make sense? So every now and then you have some sort of event that might occur that might affect a separate but dependent event, right? But, since Tyler said independent earlier, let's give another scenario. Would the probability of the second event change such that the first had already occurred? If I was talking about what's the probability of, let's see, pulling a red ace out of a standard deck of cards, if you only pull one card, and getting an A on your history test.
Say it again?
Would the probability of the second be affected by the first occurring if I said what's the probability of you pulling a red ace out of a standard deck of cards one day and getting an A on your history test the same day?
No.
No. I mean, not unless you're like, red ace, I'm super inspired. No, it doesn't matter, right?
Oh my god.
So if one happens, the other isn't going to be affected. So that's when you would still just multiply the two, but you don't have to worry because they are completely independent events. One does not affect the other. Does that kind of make sense, the difference between the two? So we could go through and we could like actually define different things, et cetera, et cetera, et cetera. But we'll just, hey, it's working again. Thank you, Lord, for at least a moment. I said that wrong. I should be thankful always. But extra thankful. And no, I should be extra thankful always. Anyway. You can still say thank you for the good things, right? And ask for grace to say thank you in the bad things. Example number 9. So, what's going on here? Random number generator computer selects 3 integers. Ooh, now 1 to 20. What's the probability all 3 numbers are less than or equal to 5? All 3 numbers. Less than or equal to 5. What do you guys think? Can the numbers be repeated?
I don't know.
Well, if a computer is just generating from like this characteristic, is it a finite number of objects or is it just more like a parameter and say, who cares, just select whatever you want? Yeah, it's more of just a parameter, so the computer can technically select randomly 555. Yeah, the chances are going to be very slim.
Wait. No, it's not equal.
If the parameters, though, just say all these numbers are legal, there's nothing telling the computer that it can't choose the same one over
No,
again.
they're not equal to those.
Not summing less than or equal to 5. Just the numbers themselves are less than 5.
Oh,
Does that make sense?
One
Got that. Can we use combinations, permutations if they can be repeated?
I don't know. I feel like that's a no.
Combinations, permutations, you have n finite objects being used, and once you use one, now you have fewer the next time for both of them. Like you have 20 people for a committee. If you select one person for president, then he can't be vice president. Someone else will be vice president. That could be like a combination. Nope, that'd be a permutation order is important. Tyler, what would you do?
Could you take 1/4 because that's the chance of it happening once, and then
Because there are 5 numbers less than or equal to 5 out of 20 possible.
yeah,
That'd be for choosing it one time though, right?
and then could you just multiply that by the same thing 3 times
Why does nothing change?
because it's not.
Numbers can be repeated.
Yeah.
So there are the exact same chances of getting it the first time and the second time and the third time, which would be 1/64. Does that make sense? So this is an example of and what you got the first time, believe it or not, does not affect, like if you got a 4, you're like, ooh, yay, I got it. If you're trying to get it for some sort of, I don't know, whatever you're trying to do.
That's a 2% chance.
Yeah, it's not much. But if you got one already, you might think that your chances are lower to get it again, but to be honest, the chances are the exact same to get it again and the exact same to get it again.
Yeah.
Which is where a lot of people go wrong in things like gambling. They don't realize is the chances truly don't change based upon, like, oh, I'm due for getting. Well, no, not necessarily. The chances are the exact same as they were the first time. What about this? Another way of saying it, instead of what is the probability, what is the likelihood? What are the chances? What are the odds? All the same, meaning the same thing.
2%.
Why?
Because it's one card out of
Oh,
52.
it's only 1 out of 52. Well, that's kind of slim pickings right there.
2% is probably.
What'd you say? That was about 2%?
That's about 2%.
Wait, isn't it 2? Yeah, it's 1.
Odds.
It's 0.019.
Gotta be careful. Is there only one red 4 in standard deck? Yeah, be careful.
Two.
Which means, we had somebody convinced though.
There is.
Struggle. 2 out of 52. 2 different suits have red cards. They didn't say specifically the actual suit themselves. That would be 1 out of 26, right? Which would be approximately 4%? 4 point what?
No. 3
Like, there's
3.8, so round up to 4. 1 over 26 or approximately 4%. Not sure I like those odds either. Alright, one more key phrase. Or keyword. Or. If you guys even somewhat remotely remember the word intersection, hopefully somewhere in the same-ish file of your filing cabinets, which is probably way back somewhere. I know, hang in there. Is the word union for or. Is the word union for or. Probability of events A or B occurring, much different than A and B occurring. Now, once again, I'm bringing the Venn diagram in specifically for saying, hey, do they have shared characteristics? This one already has a snazzy term for it, mutually exclusive. Shared characteristics are like, hey, their Venn diagrams would overlap. Mutually exclusive events would say, oh, no, they can't both be true at the same time. So if I was to ask for how many of you guys have all white shoes on, stand up, and how many of you guys have all black shoes, stand up? Is someone going to be standing up for both?
Wait, like
Hopefully not, unless, I don't know, something weird's going on with
one
them.
black shoe, one white shoe.
I said all shoes, plural. I was trying to make it so no one could counter it. Shared characteristics. If A and B could be true at the exact same time, if they were talking about characteristics, then we need to beware of the overlap. Beware the shared. Beware the overlap. And here's the reason why. If we go back to our what example was I using? The jeans and the brown hair, right?
Sure.
I'll go that way. If I was to ask, what is the probability that someone in this room is wearing jeans or has brown hair? What's the probability in this room that someone is now union? It's going to be a snazzy actual U, which is kind of nice to remember because it's union. Just some people forget that it's U for or. Probability of A or B. If I was to have everybody with jeans, stand up. Let's count them. Write down the number. Everybody sit down. Everybody with brown hair, stand up. Write it down. Everybody sit down. Add the two numbers, then divide by the number of people in the class. Would that be an accurate probability? Why not?
Small sample.
Huh? If I counted all the jeans and if I counted all the brown haired people, what did I not account for? The overlap. How many people stood up twice, so I counted them twice, but they're really only how many students? Each one is only one, right? So I count them as two different students, but they're really just one. I just double counted and my numbers are way off. So I could have a number on top that's way bigger because most of you guys have, if I was to say dark hair. So you'd be like, I have black, I have brown, I have dark brown. Anyway, stop. Coming back. The majority of you guys are brown haired and at least a few of you have jeans, probably more than the light haired people. So long story short, we would probably have a number that's higher than the actual number of students that are here today. Someone help Cameron out. It's a rough day, but the air's on. Coming back. Usually someone next to him. JJ, headphone out. You guys are my algebra 1 kids. What happened? You're juniors. Anyway.
It's Friday.
It's a Friday.
Coming back. No excuses. What we have to do is, if they have shared characteristics, take all or the probability of A happening, take the probability of B happening, and say, uh-oh, I better subtract the probability of A and B happening. I have to subtract the overlap. I have to take away the overlap. If I get all of A plus all of B, I just double counted that portion. I have to subtract 1. So if I have all the people with jeans, stand up, count. People with brown hair, stand up, count. People with both, stand up, count. I would add the first two, then I would subtract the last one, and I would have the correct number of kids, and I'd have to do my whole probability over the total. But mutually exclusive events, we're saying that the two things can't be shared. If the two things can't be shared, then A and B are totally separate. The all white shoes and the all black shoes, I can say, oh, no big deal. There's no danger there. So probability of A or B would just be take all the A over the total possible, take all the B over the total possible, and add the two together. Okay. So with that, oh, you guys still getting it? Sorry, low stand. You guys were getting really fidgety, so I figured we were right before the bell, but we're not even close. I mean, we are. Don't worry. But not as close as some of you were behaving. Remember, we want to get through this section totally today. So that Monday we have most stages to work. Just think the review can't be that long. It's only on 2 sections. Are we ready? For those of you who are ready, the next example is what is the probability of getting a black or numbered card when you choose one card out of the standard deck? That's a nice example. What's the probability of getting a black or numbered card, like an actual number on the card, not representative of an actual number? When picking a single card out of the standard deck.
Black or.
Yeah, you can use the formula, right? Think of all the blacks, think of all the numbers, and then subtract the black numbers.
Is ace considered a number?
No, dear.
Actual numbers aren't.
A. So
And A is a variable, and a variable represents a number.
Supposed to be, but it is. Oh, well, I mean, in the card game it is.
What's the probability of getting a black card? Right? Or 1/2?
Oh,
why am I doing 50 seconds? Because then I have common denominators to put together. Plus, what's the probability of getting a numbered card? How'd you find it? Yep, there are 9 numbered cards. 2 through 10, yeah? 9 numbered cards, 4 suits. 9 times 4, 36. Out of 52. Oh, hey, look! 62 out of 52. Those are the chances.
No.
You see what I mean?
Yeah.
It's not 62 out of 52. That's over 100%. And there are definitely cards that aren't black or numbered. So, what do we have to do? Subtract the, beware the overlap. The middle of the black numbered cards. So how many of those numbered cards? There's 9 per suit. Wait, you got it. There are 4 suits. How many of them are black? 2. So then 2 sets of 9 numbered cards. 18. 18 of these 36 that we counted were already counted in the black cards. So we can go ahead and say 18 plus 26 exactly, which would be 44. Can anybody think of an easier way of doing this?
Calculating each card. Seems pretty simple already.
Couldn't you just say, wait a minute, which cards aren't black or numbered? Face cards, only the red face cards. Hey, how many red face cards are there?
4.
4 times 2 is 8. Oh, take away 8 cards, it's all the rest. Look, it's the same thing. Same thing as 52, take away the 8 red face cards. Another way of thinking about it. And that actually leads into our final topic, although we're supposed to be like simplifying and stuff, huh? I see that hand. Tyler, go ahead. Okay, pack up your colors.
What?
Otherwise, if it goes like this back, then it's going to be lazy.
Why does it have to go at all?
We have 11 out of what? 14? You guys understand the struggle of trying to fit it in between 5 minutes?
Yeah, 85%.
85%. So the last concept is exactly what I just talked about. We could have added up all the ones that work, or we could have figured out the one set that doesn't work. And the one set that doesn't work are the red face
It's
cards.
11 over 13.
Oh yeah, I should divide there. Red face cards. This other way of doing it that I just did is the final topic. Oh, that's just more practice. The final topic of section 9.7. We have a whole other minute. You guys are stressing out. Complementary events. The chances of something not happening. Now, first of all, they could ask us for what are the chances of something not happening. Snazzy notation. Probability of not A. Kind of awkward wording, but you guys get the idea of A not occurring. Could be shown as A. Doesn't matter. It has to be a hook or something. It's like an NEA, but without an N. Or a tilde? That be. Anyway, half of an approximately equal sign. To find the probability of something not occurring, we can just say, hey, what's 100% minus the probability of it occurring? And remember, it's the same thing as 101 minus, same thing as 100% minus the ways it could occur. What's the chance of it raining today? 30%. Oh, cool. What's the chance of it not raining? 70%. Although some people say that maybe I'll just do it differently, so I don't know. But, cool kids, guess what?
No homework.
Basically do Monday. Monday's a work day. That way we can go over tricky examples, questions you have, play keep talking, and there stay alive. It's a good song. The old version and whatever Caleb was saying.